Hey everyone, thank you so much for watching the Weaviate Podcast. I'm super excited to welcome Ofir Press. Ofir just graduated with a Ph.D. from the University of Washington, studying deep learning and doing all sorts of amazing stuff with long context, large language models, as well as self-ask prompting and all sorts of interesting details. I first became aware of Ofir's work from a recommendation from Jonathan Frankel, highlighting this self-ask prompting, and Ofir was really, one of the first people to discover this combination of language models and search engines and this kind of tool use like thing. So I was just so impressed by this, and I'm so excited to talk to Ofir. Ofir, thank you so much for joining the Weaviate Podcast.
Thank you so much, Connor. Thanks for having me.
Awesome. So I think a super interesting topic to start things off would be to get into this long context, large language models. Like what happened? How come large language models could suddenly take in like 32,000 tokens as input?
Yeah, so for a long time, we were kind of training these 1,000 or 2,000 token language models. And for most of this time, language models weren't very good. They weren't very useful. And our goal was we were mainly judging models by perplexity. And we were kind of looking at them as like an academic question. They weren't very useful. But over the past 2 years, they've suddenly become good at some tasks. And now they're becoming useful. And now it's leaving the lab and it's starting to enter production. And one of the first constraints one of the biggest, constraints that people run into is that they want to generate a really long code file, or they want to read a really long book chapter, or they want to summarize a bunch of newspaper articles. And with most models, you're going to hit that token limit pretty quickly. And so getting models to handle longer sequences became like a really important goal for the entire community. Training on long sequences is really, really tough because it requires a lot of memory, and at some point you're going to run out of GPU memory. And it also requires probably training on longer documents, but most of the documents that we train on are crawled from the web, and most web documents are very short. They're like a few hundred tokens long. And so for the most part, even today, we're doing most of training, like 90% of training, on very short, 100 token internet or multi-hundred token, but sub 1,000 token documents crawled from the internet. And then we fine tune for just a tiny bit of training, maybe 1%, 5%, 10% of training. We fine tune on longer documents. And there's a few issues there that people should understand when thinking about building these models that can handle long sequences. So I think this all begins by understanding position embeddings. So we can talk a bit about that if you want to go there. So yeah, when the original transformer model was invented in 2017, they kind of gave you two options for the position embeddings, which is kind of interesting because everything else in the model, it's like, you got to do this, you got to do that, you got to do this. But for the position embeddings, you had two options. You had absolute position embeddings, and you had sinusoidal position embeddings. And so let's just briefly describe both of them. So when you feed in words to a transformer model, they were like, we don't want to just feed in words because then it might not know the order of these words. If I tell it, the table is blue, how will it know to differentiate between that? Actually, let's think of a sentence where the word order matters.
What was like the disambiguation? Like the boy was running outside. He went to get ice cream. I think that's a great one where it's like he is in reference to the boy from earlier, kind of.
No, but there's even better examples like uh, Ofir is teaching Connor. So word order really matters there because I'm trying to say that Ofir is teaching Connor. If we flip Connor and Ofir, that's a different. Connor is teaching Ofir is a different
Perfect
sentence. So for that sentence, we really need to know what word is first, what word is second, third, and fourth, and so on. And so the people who invented the transformer model were like, when we input words to this model, we don't want the model to just know what words are in the sentence that I'm feeding in. We also want it to know what order they're coming in, which is a very natural human, very like intuitive thing. When you're telling somebody words, you're not just giving them a set of words, you're also giving them in a specific order. It's clear that that matters. Later, like this was 2 years ago, Adi Chaviv with a bunch of other people and me, we showed that you actually don't need position embeddings. We could get into that later. But at the time, they thought that position embeddings were necessary. And so they were like, okay, how do we tell the model the order of we already know how to tell it what words we're giving it. We're just going to give it word vectors. But now we also need to give it positioning information. And so they were like, okay, here's the two options that we thought up of. The first one is called absolute position embeddings. Just like we're learning word embeddings for every word, right? So we have a word representation for cat, a word representation for Connor, a word representation for teaching. We're also going to learn position representations. So every time we input a word, we're actually going to be inputting two things. We're going to be inputting a word representation, and we're going to add to that a position representation. So in the sentence, Ofir is teaching Connor, we're going to first input the word Ofir with a position representation for position 1, and then is with the position representation for position 2, teaching with the position representation for position 3, and so on. And just like our word embeddings start out with a random initialization, right? So word embeddings, when we're done training, they kind of have meaning, right? The word embedding for teaching is close to the word embedding for taught. The word embedding for table is close to the word embedding for a chair. But when they start out, they're totally random. They're just in random places in space. So the same thing is true for position embeddings, absolute position embeddings. They start out randomly initialized, but as training goes on, the model learns certain properties for position 1, it learns certain properties for position 2, for position 3, and so on. It's probably putting position 1 very close in space to position 2 and 3, but very far away from position 500, but 500 is very close to 499 and 498. So that was their first kind of thing that they invented to add positionality, and it totally worked. So this works. But in the paper, in the original transformer paper, they talk about this. There's an issue with this. What if I train my transformer model on 1,000 tokens? So I crawl the web, I have lots of documents, I concatenate all of them up into this really long, billion token string. And now when I train, I can't train on this entire billion, did I say $1 billion? Billion token string. I can't train on the entire string at once because that wouldn't fit into memory. So what I do is I chunk it into chunks of 1,000 words. I'm training on the first 1,000 words, on the second 1,000 words, and on that. And so in the original paper, they talk about how this position embedding system might not work if I want to extrapolate to longer sequences. If I want to train on 1,000 tokens, but then process, write 1,001 tokens of code or understand a New York Times article that's 1,001 tokens. They were like, if we do these absolute embeddings and then we try to input 1,001 tokens, we're not going to have a position embedding for word 1,001. And they recognize that this is going to be an issue. And so they were like, okay, let's have another thing, and that's the sinusoidal position embeddings. So our issue with absolute position embeddings was that we had a position embedding for each word that was trained, and then when we wanted to look at more words than we saw during training, we just didn't have a position embedding there. And so they solved this by having a non-parametric function. So that's just a fancy word for saying that we're going to have a function now that has no learned parameters. It's like a deterministic, like you can write it up in Python. There's nothing learned in there, and that function, it takes a number, an int, and it returns a vector such that positions, ints that are close by, get mapped to vectors that are close by in vector space. That's it. So we're not going to get into all the math behind how they wrote this function, because it's not super necessary to understand the intuition here. What's needed is just to understand that they have this function, and you give it, like, you say, hey, what's the vector for position 15? And it's like, here it is. What's the vector for position 16? And their promise to you is that the vectors that they return are going to be close in space for positions that are close by. So those are sinusoidal position embeddings. And they also worked in the original transformer paper. Yeah, that's it. So the transformer paper, in the original paper, they actually did not look into figuring out whether these sinusoidal position embeddings enable extrapolation in practice. They enable it in theory, because before, right, we would train on 1,000 tokens, and then we would want to feed token 1001, but we didn't have one because we didn't train it with the absolute position embeddings. But now with sinusoidal, we don't need to train position 1001. We just ask for it and we get it. So they were like, this might enable extrapolation, but they never actually tested it in practice. Yeah, so that's position embeddings. Does that make sense?
Yeah, super interesting. And I think, so maybe jumping ahead to the AliBi attention, and the way I understand, watching your video is that the way is you just kind of do, the query times the key -3, -2, -1 to kind of do it back. But I guess kind of as we're talking about this positional embedding stuff, I'm still kind of missing the piece of my knowledge that understands how the kind of quadratic attention plays into this. Is AliBi this kind of position embedding coupled with some kind of new attention operation? Like, what happened to that quadratic, n squared attention that meant that you couldn't have long inputs?
Right, that's a great question. So let me piece that back into the original story. So when the original transformer was introduced, they talked about how sinusoidal position embeddings might enable extrapolation. In AliBi, we show that they actually don't, in practice, enable extrapolation. And now I'll talk about the quadratic thing. So yeah, for a long time, a lot of people were talking about how a major problem with attention is that it takes quadratic time in the length of the input sequence, but that's not actually a problem in practice. If you look at like a 7 billion, in very small models, like less than 1 billion parameters, attention might be taking up a large chunk of your feed-forward computation. But if you benchmark any model that's larger than like 5 billion parameters, you'll see that the attention computation is actually an insignificant part of the total feed-forward time. And I think that in very large, like 70 plus billion models, the total time spent on attention is less than 1% of the total feed forward time.
Hmm.
So I know that it looks kind of scary because theoretically attention is a n squared operation, but that's like a theoretical thing. The most important thing to do when building transformers is to actually look at while clock time and to benchmark the real models. And it's super important because something that's theoretically O of 1 could end up being a lot of time, and something that's theoretically O of n squared could end up being very quick. And that's what happens with large transformer language models. As I said, in the 70 billion plus param range, only 1% or less, don't quote me on this, but it's around 1% of the total feed forward time is spent on attention. Most of it is spent on the feed forward layers. And so that wasn't an issue. I know that there were a bunch of papers that tried tackling this issue by building like linear transformer models, but in my view, these papers were trying to solve a problem that didn't really exist, and none of these models actually achieved good empirical performance, and so I've never needed to use any of those types of strategies, and I've never felt that those were necessary. So AliBi is just a position embedding method. We still use the normal attention mechanism, the squared attention mechanism. And you can ask some more questions, and then I can open my slides and show you like a brief overview of AliBi.
Sorry if this is a dumb question, but
No.
So I thought the problem was when you're doing that query key multiplication, like you just can't fit that on a GPU when it's like, 32K inputs with the embedding dimension, and you end up just having this gigantic matrix. I thought that was kind of what stopped you from, scaling the inputs as big as you like.
It does become an issue at some point. So this is definitely not a dumb question, but it does become an issue at some point. Especially now when people are thinking about doing looking at 100,000 tokens at once, it's going to become an issue. So now this might be a research direction that will receive renewed interest, but all the way up to like 8,000 or 16,000 tokens, you can definitely fit that on a GPU.
Well, can you? I'm sorry to cut you off, but can you also just kind of like similar to the gradient checkpointing and like regnets, like can you just kind of like cut up the keys and then multiply the query by this set of keys? Kind of.
Exactly. It's gonna be like really, it's gonna make things slower, obviously, but you don't have to look at all the keys and queries at once. You could just, if you have 10,000 queries and 10,000 keys, you could break down this computation. You could compute every query by itself. So you could definitely do that. It's just going to be slower, but if you need to attend over a really large input, you could definitely break it down.
Yeah, really cool. So maybe we could hop into the slides now, and
let's do it.
As Ofir is setting up with this, I'd say to our Weaviate podcast listeners, we are trying a new recording software, and so if you like this kind of like half podcast, half like show something visual, please let us know in the comments, and then we'll stick with this kind of format. But yeah, it's super cool. I think this will be fun to kind of go between conversation and maybe looking at something, because I do think a lot of conversation topics, especially like as we're talking about positional embeddings, maybe kind of like seeing something might help the conversation click. Maybe not great for like people who like to listen to I think like hopefully the commentary over the slides also will still make this work, even if you're like listening to this at the gym or something where you don't really like the visual component of the podcast. But it's I think it's really interesting.
Yeah, I'll try to describe as much of this in words, so that anybody who's just listening won't miss out too much. Anyways, here's how you implement AliBi. So it's one easy step, but step 0 is to comment out the sinusoidal position embeddings. So yeah, as I said, AliBi is just like a drop-in replacement, right? There's like the absolute and sinusoidal position embeddings. There's now rotary position embeddings. So AliBi is just a drop-in replacement for any of these. So you comment out the sinusoidal position embeddings, and then the one step that is required to implement AliBi is to add a bias to the attention scores. So I just have some intuition here, but this is very obvious to all the humans that are listening to the podcast. If I have a sentence here, like the quick brown fox jumped over, and the last word is over, right? And I'm trying to generate the next word. So over is my query, and all the other words are my keys. And I'm attending to all of these previous words to try and generate the next word. And as humans, we know that when we're reading a bunch of text, the words that matter most to the current context, the words that matter most to my prediction of what the next word will be, are the words that are nearby. And as a word is further away, it matters less and less and less. And so what AliBi is going to try to do is to just encode this intuition that all of us have into a transformer language model. So instead of telling the model, hey, this is word 1, this is word 2, this is word 3, we're not going to do that anymore. We're not telling it which word is 1, which word is 2, which word is 3. We're just, for every context, we're telling it, hey, this word matters a lot. This word matters just a tiny bit less. This word matters even more or less. But and then, like, the super further away words don't really matter. So that's what we're going to do with AliBi. And here's how we do it. So as I said, over is the last word, so that's our query. And then all the other words are our keys, right? So we have all these dot products. That's how we compute attention at this current time step. And this is normal attention, right? So we compute the dot product between over and jumped, over and fox, over and brown. And AliBi is going to just gently change this by subtracting a bias from each of these dot products. And this bias is going to linearly grow as we get further away. So over and over, once is a key and once is a query, that's the same word, so there's 0 bias. And then we're going to start going further away. Over and jump, that's 1 word away, we're going to subtract 1. Over and fox, we're going to subtract 2, and so on. And this is the intuition behind AliBi, but in reality, we actually multiply this constant by a slope. It's called m here. And this is a number that is not learned. It's just a set float. Yeah, that's it. So that's what happens in AliBi. And like there's just one more small technical detail. When you do attention, we typically do multi-headed attention, right? You don't do attention just once at every time step, at every layer. You do it multiple times, right? Transformers usually have dozens of heads. And so AliBi uses a different M value for each head. So if you have 8 heads, these M values are going to be half, a fourth, and so on. It's just going to be this sequence. For 16 heads, it's these values. There's just a method in the AliBi repo that tells you which M values to use. And what this does is that when every head attends backwards to the previous words, it biases previous context in varyingly decreasing ways. So some heads are going to have large biases, which is going to mean that they're going to only look very closely nearby and not really attend to words that are far away. And some heads have very, very small M values, which means that they will look really far away before the bias becomes really big and we stop looking. Yeah, so that's AliBi.
Oh, it's so interesting. I was going to ask if this had something to do with that kind of like lost in the middle paper, because it seems like, um, when before you explain the multi-head attention, how you'd have different values for the M, I was thinking like, well, this is really biasing it towards the most recent tokens, and then that would really probably impact how you think about the kind of retrieval augmented generation and how you pack the prompt and sort of like, yeah.
Yeah, so there's a bunch of things here. So first of all, yeah, at first this kind of looks weird because it seems like we're forcing the model to only look really closely nearby and not really look far away. But we've benchmarked this against sinusoidal and rotary and absolute position embeddings many times over, and every single time we find that it beats or matches all of these other methods. So even though it looks as though we're kind of biasing to only look nearby, we're actually we're letting it look everywhere, and we're just using this bias as a way to inject positional understanding into the model, kind of give these positionality hints without really forcing the model to just look nearby. It can look wherever it wants. It just has some heads that are kind of have a harder time looking further away, but some heads they have this bias is incredibly slow over there, and so they can look far away. And so while at first it might seem like this model can't really look far away, it can. I think that we should look at this penalty, this bias, more of a kind of a hint of, oh, this word is further away. You can look at it, but just FYI, it's kind of far.
Yeah.
So there's you don't lose anything, and I mean the benchmarks speak for themselves. It works, and yeah, so that's for AliBi. And then of course language models as a whole, no matter what position embedding you use, have a very strong recency bias. And this is probably due to many things, but one of the reasons that this happens is because language has a very strong recency bias, right? You're training on all these documents from the internet, or even if it's books or whatever you're training on, most of the time, in order to predict one word into the future, you only need to look at the past 5 or 6 or 7 words. And so no matter what position embedding you're going to use, your language model is going to have an incredibly strong recency bias, right? And that's going to make it a bit tougher if during inference you're suddenly giving it 5 papers from arXiv and asking it a question that involves kind of querying all 5 of them. That's going to be tough, because most of the time during training it was completing 200 word news briefs from Reuters or something. It was doing a totally different and much simpler task. So that's an issue. That's a very big issue, but that doesn't necessarily come from the position embedding that you use. It's mostly, I think, because of how language is. Yeah.
That inspires me to ask you this question. So I'm very curious about this idea of retrieval aware training. I've seen Mosaic MPT 30 billion describes this staged training where they first train with 1K length sequences, and then 4K for say the first 8,000 steps of training are with 1K, and then the next 2K with that. But so this kind of retrieval aware training where you're training a model that takes 32K, 100K length inputs. So you kind of would retrieve from your, vector database, hopefully, and do this during training to have this model. So it doesn't have this, I'm only completing 200 word Reuters titles, as you mentioned, but it's seen this kind of thing of having just an enormous context window.
Right.
So how important do you think retrieval is going to be kind of integrated into the training of large language models.
Yeah, there's like a few different things that you touched on here that are kind of distinct. So let me break this down piece by piece. So, so stage training is a name that we invented in a paper we published 3 years ago called Short Former for a process that we did not invent, but I think we were the first to kind of explore empirically and kind of show that it really works. So stage training, to my knowledge, was first done by Bert. And when we use the term stage training, we mean that you train on short sequences for a bunch of time, and then you train on longer sequences for a minor amount of the time. So, for example, BERT is a model that can handle 512 token sequences. But if you read the paper, you'll notice that they trained on 128 token sequences for 90% of training, and then they did the last 10% of training with 512 tokens. And they did that, and then nobody else really did that. And then when we wrote Short Former, we noticed that training on long sequences at that time, with the data that we had then and the smaller models that we had then, we noticed that even though people were training on like 2,000 or 3,000 token long sequences at the time, we noticed that it wasn't really beneficial. And so we coined this term stage training, and we really explored it, and we showed that you can actually train on very short sequences, even shorter than 128 tokens, for a lot of time, and then just do the last bit of training on like 1,000 or 2,000 tokens, and you get results that are just as good as training on really long sequences for the entire duration. So that's stage training. So stage training isn't necessarily a retrieval augmented thing. Stage training just means, hey, I'm going to train on really short sequences, and then I'll train on longer ones. And that worked really well for BERT in, I think it was 2018 or 2017. It worked really well. Oh no, BERT was 2018. It worked really well for us when we wrote Short Former in 2019. And then Mosaic recently did this with one of their MPT models, where, if I remember correctly, they trained it on like 2,000 tokens for a really, really long time. And then they fine-tuned it, or they did the last bit of training on 65,000 token long sequences. So you can fit a 65,000 token long sequence in a GPU's memory, but it makes training really, really slow. And so if they would have done that for 100% of training, that would just have been probably too expensive, way too slow. And so because a lot of the things you need to learn as a language model are really in the short term. A lot of learning is just in the 100 tokens, the 100 previous tokens. So there's no real reason to train on 65,000 tokens for the entire duration of training. So Mosaic did this really smart thing where they just trained on, I think it was 2,000 token sequences, or 2,000 token long sequences for a large percentage of the time. And then they trained on the super long, 65,000 token books or whatever it was. And that's a super smart strategy. So it's still, stage training still works today. So that's stage training. And now separate from that is the whole retrieval augmented models. And then you can, I guess, combine both them. But let's talk separately about retrieval augmented models. Yeah, I think that going forward, a lot of the things that we want to do with language models will have to use some kind of retrieval augmentation. If you want to do Copilot style, code assist for really large repos, you're not going to be able to fit an entire repo into a language model's context. If you want to do medical search, you're not going to fit every medical paper that's been published in your language model's context window, not even in 2 or 3 years. Maybe in 10 years you will, but right now it's not coming anytime soon. And so retrieval augmentation is just a very clear, very simple way to kind of get the best of both worlds. Both have access to, lots of content, but also use the power of language models. So I definitely believe in retrieval augmented systems. And then the question arises of, should we do this during training or should we just do this during inference? And as you said, if you just do it during inference, you have a model that was trained on relatively shorter documents. And now during inference, you ask it to look at 5 archive papers, it's going to have a tough time. I think the solution for that is to do retrieval augmented fine tuning, or to kind of do the last bit of training with some kind of long documents that are put into the language model's context. I haven't really seen, I haven't been convinced that training with retrieval for the entire duration of training is something that's necessary, but yeah, I think that's something that people are doing research on right now, and it's a really interesting subject.
Yeah, that makes a ton of sense to me, that like you want to build up kind of representations with the shorter sequences. I imagine the throughput of getting each, training batch into the GPU with shorter samples is easier, as you mentioned, maybe like breaking up the key multiplications. So that brings me into your next really famous work that I'm so excited to talk about, is this self-ask prompting, because it's such an interesting part of retrieval, where if I ask you a question, like I think the canonical example is, did Aristotle use a laptop? And like you break this question into the two questions to facilitate the retrieval. So I'm just so curious what your current thinking on self-ask prompting, as well as kind of what inspired you to originally go down that route.
Yeah. I was just playing around with GPT-3. This was written a bit more than a year. Oh, actually a year ago. So this was before ChatGPT, before GPT-4. I was playing around with it, and I started trying to figure out if I could trick it. And so I started asking questions like, when did Israel land on the moon? Which Canadian was the first person to explore Everest? Like all kinds of questions that are incorrect. Wait, what did I say? Oh, the first person. Yeah, that's not. He wasn't Canadian, right? And it would get them wrong. I mean, since then, people have put these types of questions on Twitter. It's like a funny meme now. I like this type of stuff, but like people have asked it. I can't remember who this was. I'm sorry, but somebody asked it, when was the Golden Gate Bridge moved across Egypt for the second time? And GPT-3 is like, oh, of course, this happened on March 17th, 1984, whatever. I don't know. It's like, it really and yeah, for all those questions that I gave, like if I remember when I asked GPT-3, when did Israel first land on the moon, it would be like, June 10th, 1992, right?
Mm-hmm.
And then I was like, okay, how do I solve this? Like, there's no way that this can't be solved. Like with just purely the model, no retrieval, no Googling, no nothing. Like just the model. And I pretty quickly came up with a solution. So in the world of GPT-3, we weren't doing a lot of zero-shot prompting where you just ask it a question. We were doing more like, single-shot or few-shot prompting, where you would have a few questions, you would write your own answers, and then you would ask GPT-3 a new question that you wanted an answer to. So what I did to fix this issue with the false questions is I was like from now on, whenever I ask you a question, let's break it down into 2 steps. Step 1, try to understand if the question is truthful. And then only if it is truthful, then answer it, right? So in the example questions, I would have like a question like, when did Spain first acquire nuclear weapons? So I would have a question, when did Spain acquire nuclear weapons? And then I would be like, is this question correct? Question mark and then colon. And then I'd be like, no, Spain never has acquired nuclear weapons. And then I would have answer, colon, no answer. I'm not answering this question. Like it doesn't make sense. Right. So that's in the example that I'm giving GPT-3. And then I would ask it a new question. When did Israel land on the moon? And then it would ask itself, has Israel ever landed on the moon? No, therefore I'm not answering this question. And yeah, this worked. It managed to now all these questions that it was, when was the Golden Gate Bridge moved across Egypt? It would ask itself, has the Golden Gate Bridge ever been moved across Egypt? No. And then it fixed this issue. And that was really, really cool to me, that just by prompting, you could fix these significant issues. And I think my main lesson from there is that, I've known this for a really long time, and everybody should know this. Language models are kind of stupid, or all machine learning models are not, they're kind of good at doing what they were trained on, and they're not great at doing things that are super out of distribution. And so whenever I'm prompt engineering, the thing that I'm thinking most about is how can I break this down? If I have a task that a language model has never seen before, the question that I ask myself is, how can I break this down into subtasks such that each subtask is as close as possible to something that it has seen before? So asking it questions with false presuppositions is out of distribution, because most of the time on the internet, when people ask questions, they're not asking these absurd, silly questions. They're asking truthful questions. And so I think that's why it kind of went crazy and started like giving dates to all these like fictional events that never happened. It's because most of the time on the internet, when somebody asks a question, the output distribution is a date. Like you're not going to start arguing. Like most of the questions on the internet are totally legitimate. And it's not very common that a model observes somebody saying, oh, actually, that question is totally wrong. I'm not going to like. And so the thing that solved it was to break it down into these 2 steps of, is this question even real? And then answering it. And so that got me to self-ask. So in self-ask, the first thing that we kind of show is that language models struggle with multi-hop questions. Multi-hop questions are questions that require retrieving multiple pieces of evidence to answer. For example, when was the founder of Craigslist born? Right? You first have to figure out who the founder of Craigslist was, and then you have to figure out when they were born. And we noticed that language models really struggled with those types of questions. Who was president of the United States when Billie Eilish was born? It got that wrong. And when you look into it, you can ask the language model. So I asked GPT-3 who was the president when Billie Eilish was born, and it gets it wrong. And then I can ask it, when was Billie Eilish born? It gets that right. And then I take that data and I'm like, who was president on that date? And it gets that right too. So even though it has the facts that are needed to answer that compositional question, it has some kind of reasoning bug that doesn't really allow it to understand compositional questions sometimes. And so what we did was we took this thinking of breaking down complex things into simpler things. And so the prompt for self-ask basically says, hey, when you get a compositional question, don't try to answer it. Just try to break it down into what is the first sub-question that I need to answer in order to get to the final answer. So the first question in the Billie Eilish case is, when was Billie Eilish born? And so I'm like, okay, just write the first sub question. Great. Now what's the answer to that? It answers that, and then I'm like, okay, what's the second question that you need to answer? Who was president on that date? And then what's the answer to that? George Bush or whatever. So the final answer is George Bush. So we just have a prompt with a few examples of me doing this process, this self-ask process, with a bunch of example questions, and then you give it your own question, and it automatically decomposes it into sub-questions, answers them, and then answers a full question. And it does it better than chain of thought. So yeah, I'll let you ask some questions, but I have a bit more to say after that.
Oh yeah, I'd love to just keep rolling into the chain of thought. I mean, I love it's kind of a really great example of kind of still making the case for few shot examples. This kind of, giving it examples of when a question is unanswerable, or and generally I love this kind of question decomposition. I think it makes a ton of sense for all sorts of questions, and as people are, I think most commonly people are building like chat with your documentation, all this kind of stuff, and you can expect these kind of compositional questions where decomposing the facts is extremely useful. I guess, yeah. I mean, the chain of thought. It sounds like you have something you want.
So we talk a bunch about chain of thought in our paper. Chain of thought is super, super cool, but self-ask improves upon it. So in the paper, we show that chain of thought sometimes kind of loses its train of thought. So we have this example in the paper, and I'm not going to remember it exactly right, but it's like, who was president of the United States when superconductivity was discovered? And we'll get into retrieval and that type of stuff later, but right now we're just talking about pure, there's just a question and a language model. There's no retrieval. Whenever I say the word retrieval, I mean the language model is kind of retrieving facts from within its memory or whatever. We're not actually retrieving anything from like the web. So you have a language model and you have a question, and you ask it, who was president of the United States when superconductivity was discovered? And in the first example here, we're going to use chain of thought, right? So we have an example question with an example answer that uses chain of thought. And that means that chain of thought just means that you're like a human. You're kind of saying, well, superconductivity was discovered in 1905. The president of the United States then was Woodrow Wilson or whatever. So the final answer is Woodrow Wilson. But what happens is that chain of thought sometimes forgets what it's trying to do. So for this specific example with GPT-3, it said something like superconductivity was discovered in 1905, which is correct. And then it said the president of the United States in 1913 was Woodrow Wilson. So the final answer, or it said the correct president for 1913, but then it said that was the final answer. Do you understand? So it knew that superconductivity was discovered in 1905. It did tell us who the president of the United States was in 1930, but that's wrong. Like it was the president in 1905 was a different person, and so it got that wrong. It went off track. And so what we've learned from self-ask is two things. Is first of all, always try to decompose complex queries. It doesn't even have to be a question. If you're trying to build a complex SQL query using GPT-3, maybe try to first have it build subqueries and then combine it. If you're trying to write a complex story or marketing text or whatever, maybe try to have it first write the one perspective of it, a second perspective, and then combine them. So breaking complex things down into easier subtasks is super important. But then the second thing that we learned is that chain of thought can sometimes be problematic because it forgets where it's going. And in general, when you're generating a lot of text with a language model, it can sometimes kind of lose track of what it's trying to do. And so the second thing that we think is really useful in self-ask is that it's constantly reminding the model of what its current sub-goal is. So self-ask gets this question right because self-ask says, okay, when was superconductivity discovered? And then the model says, answer, 1905. And then it says, who was the president of the United States in 1905? And And the model says the president of the United States in 1905 was blah, blah, blah. So the answer is, and it gets it right. So by constantly reminding yourself of what your current sub goal is, we get the language model to be on track more. And so we show in the paper that our method does better than chain of thought.
Yeah, I think we all need that, right? Like, what am I doing again? Reminder of my major goals. And yeah, I mean, the whole thing, it inspires my interest. I mean, this like auto GPT, this kind of more autonomous AI, it sounds pretty natural that that's the next step. I think there are just so many interesting things you can kind of extrapolate about autonomous AI. Like you could imagine like an LLM that wants to train like a new LLM, and so it goes and it gets training data for this new LLM. Or I think maybe just the idea of like having it make pull requests to code, or like research tasks that run overnight, or running an experiment and just kind of waiting for the experiments to be done. I think there's so much to that kind of like autonomous evolution of this. And I guess kind of, I hope this isn't too off topic, but I wanted to get your opinion on these gorilla large language models as well, which is like a large language model that's been specifically trained for a particular set of APIs. And so kind of the thinking with this self-ask prompting and this query decomposer kind of concept is like, if I need to split my question into maybe a complex query, or if I need to split it into like, spinning up or like using the GitHub CLI to format a pull request, these kind of specialized LLMs in the middle seem to make a lot of sense. And it's almost like API usage as a task. Like instead of that kind of like OpenAI functions thing where you output like a JSON that has the arguments to the function, you instead have these intermediate LLMs specialized to formatting API requests. So I'm just curious if you've seen this paper, and if you think that this is an important direction going forward.
Yeah, I haven't seen that specific thing, but I can talk about my view about integrating language models with external tools. So in Self-Ask, we had this thing where we integrated it with Google Search, and we weren't the first paper at all to integrate language models with search. Google had a paper where they integrated language models with search, but all of the previous work had to do a lot of very complicated like reinforcement learning, fine-tuning for the language models in order to get their language models to understand how to operate a search engine API. And in Self-Ask, we showed this really simple thing. I don't know how we were the first to do this, but we were the first to show that you don't need to train your language model to follow a search API in order to understand how to use web search. You can just kind of trick it into using a search engine. And so our prompt is very structured. It's always like you get an input question, and then it's like, okay, sub question 1, who was president of the United States in 1905? Sub answer 1, blah, blah, blah. Sub question 2. And so what we did was we used the same self-ask method and prompt, but this time, so this system is called self-ask plus search engine, self-ask plus Google search. So we have a question like what was my question that I liked? What is the current time in the country that's hosting the World Cup? Right. So if you ask GPT-4 or GPT-3 this question, they have no chance of knowing this because I think they were trained before the World Cup happened, and they definitely don't know. So they don't know where the World Cup is happening, and then they definitely don't know what time it is right now in Qatar or whatever, right? They don't have any real-time data. And so we did this before GPT-4 and plugins and web scraping, and it's still simpler than those approaches. But what we did was we gave this question to GPT-3 with a self-asking prompt, and it was like, okay, the first sub-question I want to ask is, what country is currently hosting the World Cup, right? And then it's like answer : and then we stop it. So it's about to answer itself. We stop it. We go to Google. We extract the first question that it asked. because it's really easy to extract, because it literally says, sub question 1 colon. So super easy to parse out. We send it over to Google. We used SERP API. And then Google gives you back an answer. And then we just take that and we put that into the language model prompt, and we're like, here's the answer. So the language model thinks that it asked itself and it answered itself, even though it was Google, but it doesn't know that. It doesn't need to know that. And that's like, okay, sub question 2, what is the time in Qatar? And we're like, oh, wait a second. We pause it. We take that question, parse it out, send it to Google. Google tells us the answer. We put that back into the prompt, and it says, okay, the final answer is, 7 p.m. So yeah, we did this like a year ago, and it's super simple, and it's really, really useful, and it's super powerful. And a lot of the previous approaches had to fine-tune language models. I think one of the previous papers, for some reason, they needed like humans to they had to kind of use like human annotators and record how they did Google searches in order to use that to very, very complex stuff. We did none of that. It was all super, super easy. But yeah, I'm very much in favor of simple solutions. I've been using GPT-4 to write Python code for me, and it's almost always executable, and it almost always runs. And then whenever it's not correct, I'm like, hey, it returned this bug or whatever, and then it just rewrites it for me. Sometimes it takes it like 10 tries, but at some point it will return something that's, I think for like 70% of my questions, it ends up returning correct code. So I'm not sure that right now I see a need for specific language models for specific APIs. I would just include like the API in the prompt, or the relevant function calls in the prompt, and ask GPT-4 to program for me. But yeah, if you want to automate this, it's not currently, as I said, only like 70% of the time does it return code that runs. So it's not something that would, you couldn't put this in production and expect it to work all the time. But I don't currently see the benefit of fine-tuning your own models on your API.
Well, I think to speak to a bit to the Weaviate case is like I think one of the big things about these vector databases is kind of adding like symbolic filters, like where do you want to search? So like, if you say, what's the latest opinion on AliBi attention, and whether you want to search Twitter or X, sorry, if you want to search X or if you want to search archive, and then you could, tailor the search accordingly. Maybe you want to add a filter to that one, like date is greater than July 5th, 2023, or something like that. And then I think one other important kind of lever for formulating these queries, and the reason why you would want an LLM that knows how to control the API is, is this a vector search query or is this an SQL query? So I think there are cases, I love that reflection prompting thing, like where you get the output from the code executor and then you just keep chaining that. And I think that could also work with search, where you could get the search results and say, okay, do I need to re-rank this, or should I actually use like a hybrid search between BM25 and dense vector search? And I think I think the whole topic, there's quite a lot of interesting things with this. But yeah, so kind of another topic is, at the end of your dissertation, you were talking about new directions for new training data. And you just mentioned kind of, I think we were all just wildly impressed by how well it can write code. And I think kind of, it's extremely powerful. Like, as we're talking about this topic of like autonomous AI, I just love how with code, it can come up with whatever experiment it wants, kind of. So it's like this kind of exploration, exploitation, like the, reinforcement learning, all that kind of coming into it. How do you see that kind of language models trained on code, and how that could change everything?
It seems like code is really critical for building strong language models. I mean, we still haven't really had a very good, thorough, large empirical evaluation of this. But it might be that the reason that GPT-4 is so good at tasks that aren't even programming, like it's really good at summarizing like math papers. Like, why is that happening? That might be because it was trained on a lot of code. Code might make models smarter. We don't know yet, but that's a hypothesis a lot of people are throwing around. I'm just, I know that lots of people have been using LMs for like, legal stuff. People are trying to show that language models are really good at answering medical questions. And I think that might be a very big use case in the future. But the current thing that I'm most excited about is code assistance. Because, I mean, almost everybody that I know is using AI to help them program right now. It's already made such a big impact. But there's still a lot more to do there. So a lot of the time, GPT-4 will program something incorrect, and I'll show it like, the runtime errors, and I'll tell it, hey, it's not, this isn't good, this isn't okay. Like, and we'll be like, sorry, what about this? Sorry, what about this? And like, we'll be in like this infinite loop that never ends of just incorrect proposals. So there's still a lot to do there. It's not at the place where it can automatically do things correctly. We're far from that. I give it a function description sometimes, and it hallucinates things that I never asked for. Sometimes it's trying to be smarter than it needs to be, and then ends up writing like silly code. So yeah, there's a lot to do there. We still have a lot of understanding that needs to be achieved in getting language models to hallucinate less, to be more consistent, right? A lot of times, so in our paper, we showed this, in the self-ask paper, we showed this silly example of like, GPT-3 with chain of thought saying superconductivity was discovered in 1905, the president in 1913, was like this huge inconsistency. Like, we were asking about like the president in 1905, why'd you go to 1913, right? In a very short context. It's not like it had said 1905 at the beginning of the page and then written like 17 pages and then it went to 1930. No, it was inconsistent within like 7 words, and that was a problem with GPT-3 a year ago, but it's still a problem right now. And so yeah, there's still a lot to be done there. Yeah, but I really like the programming aspect.
Yeah, I guess kind of just something that sorry to be kind of coming back to that other topic, but like with the ability of the language models to write APIs,
yeah,
it's like if as you're fine tuning it for the API, it loses that ability to have like that reflection, like see the output, see why it failed, and then kind of revise it accordingly. There's all sorts of stuff going on with like structured output parsing and trying to force the output almost like a compiler, like to follow the grammar such that it, you would only sample tokens that follow the acceptable grammar. And yeah, I think it's all just such an interesting direction, writing code. And the code interpreter, I think, is just getting so many people's imaginations on what this kind of stuff can do. And I love using it to just like, I could just grab a bunch of data, and then I can ask it, hey, could you parse this out and turn it into a CSV or visualize it? And I think all of that is just incredibly powerful. So one other thing is talking about the potential of video transcript data. Can you tell me a little more about how you think that's unique from the internet text data and the opportunities there?
Yeah, so there's another rumor going around that OpenAI trained GPT-4 on transcripts of YouTube videos. I think there's a bunch of benefits there that you might not have in like your typical language model training data. Some YouTube videos, like podcasts, are really long, and they're conversations about the same topic that maybe make references to something that was said 30 minutes or 40 minutes ago. So that's really gold for language modeling. For a long time, all of the text we had was like really like had short, was either incredibly short or was slightly longer, but it wouldn't have long term dependencies. And so as we're trying to build language models that can handle more complex tasks, like analyzing a large legal document or taking like 5 code files and figuring out how to write a 6th file, as we're trying to make language models handle these more complex tasks, we need training data that challenges our models during training as much as possible. And it could be that long YouTube videos or long podcast transcripts are a way to get a lot of that training data for cheap. Yeah.
Yo, that's music to my ears, because my favorite like project is to take these podcast transcriptions and like build up the semantic search index with them, and try it through RAG. And I mean, I think it's so interesting. Like if you took these podcasts, like the Weaviate podcast, and you made that the data set, you probably and then you're retrieving from some other information source, you probably want to tag it with the date as well, because maybe some new information, some new perspective is discovered from later on, and
Yep.
you retrieve that. But yeah, I love it. I think I love that angle of where do we find this kind of long context data. And yeah, this whole conversation, Ofir, thank you so much. This coverage of AliBi attention, showing the demo of how it's computed and how this enables extrapolation to longer sequence lengths. I think the self-ask prompting thing is just so powerful. I think still kind of the jury's out on how to really maximize it in these kind of auto GPT, this more autonomous kind of query decomposition and tool use. And then I think these perspectives on what we can get by more training data with code and video transcripts is also exciting. Ofir, thank you so much for joining the Weaviate Podcast.
Thank you so much, Connor. Thank you so much.